Precipitation measurement is particularly important. We need to know a lot about not only the kinds of devices that are available to us to measure precipitation, but also what their strengths and weaknesses are, and what kinds of data they're actually reporting. So here are a few questions. First, what's the most commonly used type of rain gauge in volunteer weather monitoring networks? What's the difference between a manual and an automated rain gauge? What are the strengths and weaknesses of different gauges? And what are the sources of error in rain gauges? Well, it's important to remember one thing about precipitation measurement. First, almost all precipitation measurement reflects measurement at a single point on the landscape. While we may wish to extrapolate from that single point to an area, the measurements are actually made at points, and we need to have confidence that the measurement at a single point actually corresponds with the amounts of rainfall that might be received over a much larger area. This is often difficult to do. Some of the important characteristics of precipitation measurement include the type, whether it's rain or snow, the intensity, that means the amount per unit time, the duration of the rainstorm or the snowstorm, the distribution over the landscape, and actually the amount, especially the amount reported in linear measurements like inches or millimeters. So let's talk about a couple of different kinds, general classes of rain gauges. They include manual reed gauges, like this cylinder mounted on a post, and automated stations, like this ROS station in Dog Valley in California. First of all, this is a standard 8-inch rain gauge used by the National Weather Service and actually used by many volunteers in the volunteer monitoring networks that extend across the country, but that are actually very active in the state of Nevada. It's a very simple gauge that works on a very simple principle. It actually catches rainfall through a funnel in the top, and then by the use of a smaller tube in the middle, amplifies the amount 1 to 10 so that we have a greater resolution of measurement than we might have if we just simply filled up the can with rainfall. The major components include a measuring stick, an overflow can, a collector funnel at the very top, and a measuring tube into which the measuring stick is put. And the funnel and the tube enhance measurement resolution. And they do this by having a differential diameter. The diameter in the funnel that carries water into the measurement tube in the middle is about 10 times the diameter of the tube in the middle, which gives us then an enhanced resolution, a resolution that's a factor of 10 different than it might be if we just filled up the can itself. Some of the strengths of the 8-inch rain gauge include no moving parts. It's very durable, it's well tested, it's standardized, the resolution is good, it's stable and predictable, and it's very low maintenance. Hardly anything can go wrong with it other than having it tip off level or having it be the throat at the top be filled with debris, leaves for example. Some of the weaknesses: you can't get intensity data from an 8-inch rain gauge. It's only going to give you the data that correspond with the time interval that we use to read the result from the rain gauge catch itself. It doesn't work for snow. Snow tends to plug the top and then bridge over the entire thing like a big ice cream cone, so that we end up having snowfall that sloughs off or is blown off before it can actually enter the tube in the interior. It has to be read by hand, which means we have to take it apart every time we want to do a reading, and the data reporting interval is entirely dependent upon the observer. So we can't do a pre-recorded or predetermined data recording interval. It's really determined by how often the observer gets out to take a look at it to record the. A true check rain gauge is another kind of rain gauge that has a unique feature, which is that because it's wedge shaped, it actually has very high resolution measurements at the bottom of the gauge. So if we have very low amounts of rainfall, we can read them with a high degree of accuracy in the bottom of this wedge-shaped gauge. As the gauge fills, the resolution becomes lower and lower, but for areas like Nevada in which we have rainfalls that are often in the trace amounts, the TrueCheck rain gauge is a very good tool for recording very low volume rainfalls. Some of the strengths of the TrueCheck gauge include no moving parts. It's very durable, it's well tested, it's inexpensive, it has good resolution for low yield storms and very low maintenance. Some of the weaknesses include that you can't get intensity data again. It doesn't work for snow. It has to be read by hand, and as before, the data reporting interval is entirely dependent upon the observer. We can't program that in advance. Automated gauges include the tipping bucket rain gauge. The tipping bucket gauge operates on a very simple principle. Water enters the upper funnel. It's carried down through the throat of the funnel, and then it enters something that's like a small seesaw. This has a small bucket. The seesaw is a bucket actually that has two compartments, one on the left, one on the right, and as each compartment fills, the mass of water is sufficient to tip the seesaw over. When the seesaw tips over, or when the bucket tips over, a magnet passes by a reed switch. The reed switch sends an impulse to a counter, and then we use the number of counts to estimate the total volume of rainfall, because each bucket represents a specific amount of rainfall that passed through the upper part of the funnel. In most cases, the resolution of the tipping bucket rain gauge is about 0.01 or 1/100th of an inch of rainfall. Some of the strengths of the tipping bucket rain gauge, and these are widely used throughout the United States, is that it can produce intensity data. It's usually durable and very well tested. The data can be stored or transmitted off-site when we have an automated station like the one pictured here. And the resolution is equal to or better than an 8-inch rain gauge. The weaknesses include more moving parts and the need for a power source. It has to be altered to work for snow. As it is, just like an 8-inch rain gauge, without a heated upper catchment surface, it doesn't work well for snow. It's also expensive, especially for off-site data transmission, and requires a substantial amount of maintenance, especially for maintaining things like the pivot points in the tipping bucket. Other gauges available include weighing gauges and optical gauges. The optical gauge, shown on the right, actually sends a laser beam across a small distance. There's an emitter on one side and a receiver on the other side, and because of the optical properties of the laser, it can measure both droplet size and droplet volume. Very precise, very expensive, and therefore primarily used for research purposes. The weighing gauge on the left-hand side has a long and distinguished history as part of experimental watersheds in the United States. It operates on the principle that volume of water can be represented by mass, and that as mass accumulates in a bucket, that mass can actually then be used to not only determine the volume of water and the number of inches of water that have accumulated at a certain point, but also the intensity by looking at changes of mass with time. Weighing gauges also have been outfitted to do snow sensing as well, fitted with melting surfaces on the upper part of the rain gauge that then actually funnel melted water down into a bucket that has a chemical in it such as antifreeze to keep the bucket from freezing. Some of the sources of error in measurement are important to understand. If we look at the right-hand side, many of the things that affect measurement and measurement accuracy have to do with turbulence created by the surface of the gauge as wind blows across the top. So wind currents actually can not only create turbulence, but they create turbulence that might create a shielding effect that actually blows raindrops out or actually deflects them from entering the rain gauge itself. Orifice size is very important. If the orifice on the top is too small, there's not sufficient area for water to enter. If it's too large, we have problems with evaporation. The plane of capture is very important as well. It should be parallel to the land surface or level, so that the orifice that's presented actually has the maximum area. The height above the land surface is very important. Proximity to vertical features is very important. And splash in and out can create errors in measurement as well as evaporation. Evaporation also creates errors in measurement. And vandalism. Vandalism can be an important way that data are lost and not recorded because of, for example, shooting or destruction of the station itself. Wind baffles are a good way of deflecting air currents to avoid the levels of turbulence that can blow gauges, can blow precipitation out of the catch area for the rain gauge. Here you can see these wind baffles. The gauge is set slightly inside. The turbulence, the effect associated with turbulence is avoided because of the way that the wind is actually transformed or actually funneled around the very top. The wind velocity is lost, and we lose the effect of upward velocities caused by little turbulent eddies above the sharp lip of the rain gauge. Orifice size and orientation is also very important. The area should be a minimum of about 700 millimeters squared. Small diameter gauges really aren't suitable for snow. However, one of the things that makes this a useful point to consider is that remember that not only are small diameters not suitable for snow, but many gauges actually do not have the capacity to measure snow because snow freezes in the orifice and can't actually pass through, and it actually might be a place where snow sloughs off or is blown away as it sits there and accumulates. When we have large orifice sizes, you can also have greater amounts of evaporation loss. The orifice has to be level in order to provide the most consistent catch. In terms of height above the land surface, gauges that project upwards produce wind currents that deflect precipitation, or can. When we put gauges at the soil surface, they yield somewhere between 5 and 15% more than unshielded standard gauges, which gives you a sense of how much of a wind effect there actually can be. And distance to vertical obstructions is very important as well. When we place a rain gauge, in general, we're trying to estimate the amount of rainfall that falls at a particular surface. We need to avoid obstructions such as houses and vegetation by essentially having a cone that has an angle of about 45 degrees projected upwards from the gauging station, and within that cone there should be no obstructions that would actually capture rainfall before it can enter the rain gauge itself. Splash and evaporation. Well, when we have deep gauges, we can prevent excessive evaporation and splash losses. But when we talk about so for ground level gauges, in-splash can be prevented by structures at the soil surface, for example, a small curb. But this is a very important one. When we talk about any kind of a rain gauge, whether it's a rain gauge that's associated with, or that's one we make ourselves, or one like the True Check or the 8-inch rain gauge, if we're not going to be observing the rain gauge or getting the measurement from the rain gauge, a small layer of oil can be added to prevent evaporation. And generally this is mineral oil that's added in a very small amount, just to float, enough to float on top of the water surface so that evaporation can't occur. So back to our questions. What's the most commonly used type of rain gauge in volunteer weather monitoring networks? It's the manual read gauge. And generally that's a version of the 8-inch rain gauge. So most of the data that we see from the volunteer weather monitoring networks in the state of Nevada and elsewhere comes from a manually read 8-inch rain gauge. or some version of that. The difference between a manual and an automated rain gauge, well, one of the primary differences is that both will record quantity, but only an automated rain gauge with a tipping bucket can actually record intensity. There are other differences as well. A manual gauge is very simple. It's very easy to operate. It's very easy to get accurate observations from a manual read rain gauge. However, unlike the automated rain gauge, the manual gauge can't produce intensity data. One of the other differences, though, is that the automated rain gauge can store and produce data that will give us not only intensity, but also, for example, it might give us a month's worth of data storage at a time before we have to actually go out and do maintenance or download the data to a computer or some other source. So the manual stations are cheap. The automated rain gauges are generally expensive. The manual gauges rely on hand operation, which means they're limited by the kinds of training and the dedication of volunteers. The automated rain gauges are not limited by that, but they do require a certain amount of maintenance per year to make sure that they function properly. The strengths and weaknesses of the different gauges, well, part of that again has to do with being able to record intensity, the costs of the automated rain gauges versus the lack of cost of the low cost of the manual gauges, the maintenance requirements of both, simple maintenance for manual and more complicated maintenance for the automated rain gauge. And finally, what are the sources of error? The sources of error are many. They include just simple function of the rain gauges themselves. They can actually clog with leaves and other materials so that we have a reduced catch. But apart from that, some of the other sources of error include error due to wind turbulence, error due to obstructions outside of the rain gauge, for example, sighting too close to a building or a plant, and as well as error associated with having the gauge not level. And so there are several different sources of error in rain gauges, and they include not only the function of the gauge, the way the gauge functions itself, but also external factors like wind and placement and maintenance. So it's important when you start looking at data from specific sources, and we'll look at data from the RAWS network, to have a sense of what the data ought to look like before we simply take them and apply them for different kinds of analyses, because there can be, and there often are, substantial sources of error in rain gauges that can provide us with deceptive results.